Okay, so for the last video regarding normal distribution, we're going to be testing, using hypothesis testing, the mean, okay? So the way we're going to be doing that is we're imagining taking a sample from a population and the means themselves would actually be normally distributed. That's how we get this part here. So you can see here, this X bar now is now referred to as the sample mean. And we can say that the sample mean itself is going to be normally distributed, with mu being the same mu value, but variance now being sigma squared over n being the number of samples. Okay, so this is how we're going to do a hypothesis test for a mean. And so as you can see, there's a code for standardizing, all right? There used to be x minus mu over sigma, but for this, we now slightly change this to x bar minus mu over sigma over root n, okay? And this is a code to standardize for the mean. This is useful for later on when we're trying to find the critical region within our hypothesis testing. Right, so let's try this question here. So we have the daily mean wind speeds is modeled as being normally distributed with standard deviation of 3.1 knots. A random sample of 25 recorded daily mean wind speeds is taken at Heathrow in 2015. Given that the mean of the sample is 12.2 knots, test at the 2.5 level of significance whether the mean of the daily wind speeds is greater than 2.5 knots. So first things first, H naught. Our mean value that they originally thought would to be correct was going to be this 9.5, right? And they're saying test whether it's greater than 9.5. So therefore H1 would be when mean is greater than 9.5, like this. We can now work out our distribution. So X bar is going to be normally distributed with mean of 9.5 and variance of, just remember, it's sigma squared over n now, right? So the standard deviation was 3.1. So 3.1 squared over n being the random sample of 25. Okay, so this is our distribution. The significance level is 2.5%, so it's going to be 0.025, like so. And so now we can go about doing the test. Okay, so in the sample, they got 12.2 knots. So that essentially is going to be our X bar value, which is 12.2. So remember, there's like for the hypothesis testing video series, they can do like the probability or you can find the critical region. I'm going to just do both methods so you guys, it's like a reminder for you guys. So let's do the probability method. So we have to try and find the probability that X bar 12.2 is larger than 9.5. That's how we know. And also because it's bigger than 9.5, we find bigger than 12.2. You can use the calculator using the correct parameters and you get a value of 0. So we know that 0 is less than 0.025, the significance level. So therefore we are going to reject our null hypothesis. We can also use the critical region method, right? So critical region. So I'm going to draw my bell curve like this. Because it's larger than one-tailed test, we're trying to find this A value here. So we know that the probability that X bar being bigger than or equal to A should be less than the significance level, so 0.025. Now the way we're going to find out A is now we're going to standardize it using the code. So remember the code Z was equal to X bar minus mu over the sigma over root n. So this is now going to change to probability that Z is going to be bigger than A minus mu. Mu, as you can see, is 9.5 over the sigma is 3.1 over root n, so root 25 is going to be equal to less than 0.025. Now you can rearrange to find, or you can use an inverse normal calculator to find what this is going to be. So I can say A minus 9.5 over 3.1 over root 25 is actually going to be equal to 1.96. And now I can rearrange and you find that A is going to be 10.715. So the critical region is when X bar is bigger than or equal to 10.715. The value they got in the sample, remember, was this 12.2. So 12.2 is greater than 10.715. So therefore we get the same conclusion. We reject H naught because it's within the critical region. Okay, let's just try one more. So the diameters of a circular cardboard drink mats produced by a certain machine are normally distributed with mean 9 and standard deviation 0.15. After the machine is serviced, a random sample of 30 mats is selected and their diameters are measured. The mean of the sample was 8.95. Test at the 5% level of significance where there is a significance evidence of a change in the mean diameter. So you should realize now H naught, first things first, H naught originally was mu is 9. H1, this is actually a two-tailed test, right? Because it's asking for a change, doesn't really specify whether it's bigger than or less than. So therefore mu would be not equal to 9 like this. Our x-bar distribution will be normally distributed. Mean originally was 9. Variance is 0.15 squared over n, so it was 30, so over 30. Our significance level of alpha is 5%, so 0.05. And the x-bar they got from the sample was 8.95, right? This is what they got from the sample, our test statistic. Now it's a matter of just finding it. So once again, I'm just going to do both methods. So probability, so the probability method first. So we're trying to find the probability that x-bar, as you can see, 8.95 here is less than 9. Okay, so we should be finding less than 8.95. Okay, and you can use this. You can use the calculator to find this. So this comes out to 0.0339. 0.0339 is less than or bigger than 0.025. Remember, because it's a two-tailed test, we should be dividing this by 2, right? Because it's a two-tailed test. That's why you get this 0.025. So therefore, we do not reject H0. Again, I'm also going to do the critical region method. So I'm going to draw my bell curve like so. Because it's a two-tailed test, we now have two sections here, right? So we have this A and this B, which we have to find. So we know that the probability that x bar is less than A should be less than 0.025. And the probability that x bar is greater than B should also be less than 0.025, like this. To find this, we have to standardize it. So for the first one, we'll get probability that Z is going to be less than A minus mean. Mean is 9 over 0.15 over root 30 is equal to 0.025. And the second one will be probability that Z is going to be larger than B minus 9 over 0.15 over root 30. It's going to be equal to 0.025 as well. And then you can get the equation using the inverse function from the calculator. For 0.025, you get a value of minus 1.96 for this one. And for the second one, B minus 9 over 0.15 over root 30, you get a value of plus 1.96, which you can just rearrange to find A and B. A turns out to be 8.946 and B comes out to be 9.054. And so we'll reject it when x is less than or equal to 8.946, or when x is going to be, x bar, should be bigger than or equal to 9.054. Now what we got from the sample, the test statistic was 8.95, right? So as you can see, 8.95 is going to be bigger than 8.946. And 8.95 is less than 9.054. So it's not in either of the critical regions. So therefore, we do not reject H0. So as you can see, we still get the same conclusion. It's just two different ways of working out whether we reject it or not. So this is the last video regarding hypothesis testing for mean. It's just using the fact that when we create a sample, the means themselves will follow a normal distribution. But the way of actually testing whether it's insufficient or insignificant is all the same as we've been doing before.